Okay, next up we have Edward, who will be presenting superpixel compilation for pixel processor arrays. So Edward, if you can share the screen.
Just getting there. Moving around on my windows. There we go. Is that up?
Yep.
Cool. So yeah, thank you for coming to listen to my talk about superpixel compilation for pixel processor arrays. It's by me and Paul Kelly, Department of Computing, and we just want to thank straight off Riku, Piotr, Stephen, Jingyang for their support and collaboration with practical stuff with the SCAMP5 device, and yeah, all that sort of help. So really, this is a story more about compilers than division systems. Basically, the idea is that we want to make it easier for people to take their convolutional kernels and actually get them running on focal plane sense processors, in particular SCAMP5. So a small quick recap of what SCAMP5 is. We have a 256 by 256 array of processing elements, and each one of these elements has its own little pixel. And so this is a massively parallel SIMD design where every processing element is going to be receiving and executing the same instructions at the same time. What's one of the limiting factors here, though, is that on the digital side, at least, we are working with 1-bit binary registers. So this means everything we're doing is got to be in bit serial, which for doing convolutional networks can be complicated because we want to be able to add up lots of values and multiply them and things. And the second problem is that we only have 14 binary registers, and only 7 of them are actually general purpose. So one of the big key things we're trying to do is allow us to leverage more memory by making compromises on things like resolution. So superpixels aren't new for us, by us. So Bose et al. Just showed that you can make a 4x4 square of these processing elements, and using this sort of squiggly pattern, you can fit a 16-bit value. So one of the main differences that we're proposing is that in Laurie's work, they use ternary weighted convolutional kernels, and they put those ternary weights into the memory of the SCAMP processor. Whereas what we do is we encode the weights, not just ternary weights, but any quotient weight really, into the instructions instead. And so this means we can actually run much deeper networks because we're only limited by the number of instructions, which there are a few quirks around, but in theory, we're not limited to just those ternary weights. So one of the main points is that it's an extension to Cain. So Cain is a compiler that we built to effectively do the similar compilation job, but on the analog side of SCAMP4. So what it does is it takes a convolutional kernel or multiple convolutional kernels, and it finds common sub-expressions that then we can use to more efficiently implement the filters on SCAMP5. So the idea is that we extended Cain to use an alternative instruction set, which is based entirely on what digital operations are available. And then we can use that for superpixels using the digital side of the SCAMP5 architecture. So really, this is the main process. We want to take, we want a system that allows anyone to supply a convolutional kernel, run it into Cain, giving, and they can supply what the actual data layout will be. So in Laurie's work, they had that 16-bit system. Here in this example, you can see there are actually a 4x4 superpixel with 4 different 4-bit values at every register. And so what we're able to do is make this trade-off between what resolution we want the whole image to be, what bit depth we want, and how many computational registers we want at every superpixel. And so there's a 3-way trade-off that we're trying to enable people to explore and find the right solution for them. And by putting it in an automatic tool, we hope that people are able to find the correct one that works for their situation. So the big point here is that there's data layout flexibility. So you see there's lots of different ways you can lay out bits. One of the key ideas here is that everything's done in a bit serial fashion. So every processing element is responsible for one significant bit of a number. But what we can do is you can have them all in one, like a 4x4 there with a 16-bit, or we could break that into two 8-bit sections. And so we could call each one of these a different bank. Because of course you have 7 digital registers. So every bank, say, has 7 computational registers. And in that 8-bit Bose photonic design, there are 2 banks. So that gives us a total of 14 computational registers, which is obviously a lot better than we get when we just have 7 1-bit registers. And of course, you can scale this this flexibility up for any sort of size superpixel, from 2x2 to 8x8 to 16x16. And of course, some of the problems grow and get harder when you get larger. Some of the problems actually get easier because there are more registers, or because you've got larger values, and so you don't overflow the numbers as much. So what's next? There's always more optimization work to be done. There are lots of things that could be made faster and more efficient. We could co-optimizing for the instruction memory size. So there's a problem we have at the moment where the amount of memory, of instruction memory it takes to store these long sequences is a big problem on the current devices. And so while we think, this shouldn't be a bottleneck for future designs and future microprocessors, it is one for current sizes. And so there's some work to be done to optimize that. And then there's the whole spectrum of work about thoroughly evaluating different designs, and with the instructions that we have, which ones are more efficient and worth looking into more. And then there's also the question of what we can do in the hardware to make what changes we could do in next generations of SCAMP-like devices that would enable faster and more efficient use of these data layouts. So if you have any questions, you have to answer them.
Thank you, Edward, for the talk. Well, I'll start off with a question, which is, you talked about being able to support different data layout, data bank layout. Is that optimized, or is it something which the user feeds into the system? And if it is, do you reckon it can be extended to automatically choose which layout is the best, for example?
So at the moment, what you can do is you just specify which processing element you want to be in each bank and which bit position you want it to be in. And what Cain will do is it'll try and optimize the various high-level instructions like addition and moving based on those based on what you design. So for example, when we do addition, we have to do, because it's a bit serial, we have to do a sequential carry addition. So you select one PE at a time and go round to do the carry bit. And we can optimize that, and Cain will automatically find a somewhat efficient route to doing that. As far as in the future optimizing for the user, I think that's a whole nother design space. Mm-hmm. There's a lot of work, there's a whole other design space, because you've got to think about whether or not your values are overflowing, if you need saturating arithmetic or things like that. And you need to know what sort of values you're putting in to know. So there's a whole world of pain there if you were trying to automate that process as well.
I see. So the next question is, I think Cain used to only support analog instructions, and now the superpixel idea mainly is about digital register manipulation. How much of the heuristic from the original Cain is used to optimize the superpixels?
So as far as the infrastructure goes, it's basically the same infrastructure of the compiler that does the common sub-expression finding and the fastest routes. But instead of just being able to have an add instruction like we have in the analog side, we have to make an add instruction out of like many NOR and OR instructions, because that's all that's available for the digital side. So in that phase, Cain is working on the high level instruction of adds, and then it converts that into the lower level instructions of NOR and OR, and it tries to optimize those separately. So the first half is pretty similar, and we don't. And but in none of this work, we actually changed the heuristics needed because we decided that that would be too much while we were developing it.
So just to make sure, this means that this idea can still support multiple kernel filters. So if I feed the system like 3 different kernel filters, it will try and find the common sub-expression.
Yeah, so one of the big ideas here is that because we now have more registers, then we can definitely support more and more kernels all being compiled at the same time. And that should help because there'll be more registers, it'll be able to find more efficient solutions.
I see. Well, I guess another thing to ask might be, so currently we are using this ideal superpixel because the number of registers is limited. But say, for example, we just 4 times the number of registers available on the chip. Do you reckon this ideal superpixel will be still valid then, or do you reckon it's just easier to use the available registers?
So I think if you only 4x it, then it'll still be valid. Because if you think about this, in a 4x4 superpixel, you're sort of 16xing the amount of memory per pixel.
Oh, yeah, of course.
If you manage to 16x the number of binary registers per pixel, then yeah, you can you might start thinking that actually it's not worth it. But by the time you've got that much memory, you might also be thinking that why is there not a built-in arithmetic sort of 8-bit or 16-bit add?
I see. Well, I think thank you very much for the talk.